Well, thank you all for coming. I'm on my second year of the PhD, and I'm doing a joint PhD between the University of Edinburgh and the University of Granada in my home city in Spain. So I'm going to speak about thermodynamic in wave energy. This is the list of contents I'm going to speak about. So I'm working particularly with oscillating water column, that I think most of you know how it works. But my research can be applied to every kind of wave energy converter that has a air phase or air interacting with the turbine. So all authors consider the air in the OWC chamber as dry. So this is easy because then you can characterize it as an ideal gas. This is a photo of the OWC in Mutriku, Spain. This photo was taken in 2009, like 2 or 3 months before the turbines were placed in the holes. And as you can see, the water is all coming up the orifices, so it's not dry. So what I'm doing in my PhD is study a new gas approach to see what's really happening in the inside. Let's start with the theory. So I warned you, my thesis is mainly theoretical, I'm sorry. So let's see a bit of equations. The first question I made myself when I started is, what is my OWC, my chamber? It's going to be a polytropic system. As the word says, it's a system that can take a different form depending on the shape we give to the equations. So it's adiabatic, it's isothermal, isobaric. Let's start with my assumptions. I consider that there is no heat exchange with the surroundings of the OWC, so it's like an isolated chamber with a little bit of atmosphere. This is a definition of an adiabatic system. And the previous authors also consider an adiabatic system. As you can see, PVN constant, that's the equation for the adiabatic system, for a polytropic system in general, and gives me a relation between pressure and volume, with N being the polytropic index. And they also consider that the gas inside the chamber, as I said, was drier, so could be considered as an ideal gas. And then they use the ideal gas equation that you might remember from high school. This gives a relation between pressure, volume, R is the universal gas constant, and T is the temperature. And then, particularly for an ideal gas in another adiabatic system, the polytropic index N can be defined as the fraction between the specific heats and used to be 1.4. So we can see that the polytropic index is quite important because it gives the shape of the adiabatic equation. If we change these values of N in the polytropic equation, you can see that depending on these values, my system takes one form or another. But I'm speaking about isothermal adiabatic, a lot of concepts, and you can see that it's easy to see that isothermal temperature is constant, isobaric pressure is constant, but what is constant when my system is adiabatic? There is no iso anything. So we need to do another consideration, and this is reversibility. Then we can say that entropy is constant. My OWC can be considered as reversible if we study the OWC as independent cycles of waves. So the only point where the previous authors and me, when we differ, is the idealization of the gas. And my question is there anything ideal in this world? Well, probably, but not in this thesis. So let's go. What I'm going to do is develop equations for an adiabatic system in a real gas. As you can see, the important fact of my thesis is the polytropic index N. So if the gas is real, then my polytropic index is going to be real too. Let's compare then the ideal gas and the real gas. as I said before, the ideal gas has the ideal gas equation. I always work with molar volume because then I can forget about the number of moles. That is something that, well, engineers, I think, we don't really trust. And for the real gas, we have the virial equation of state. As you can see, it's quite similar to the ideal gas equation, but we have the compressibility factor that depends on pressure and temperature. And it's a way to compare the real and the ideal gas. This equation can be expressed in this way in terms of the virial coefficient that only depends on temperature. But both ideal and real gas have in common the polytropic equation, as we saw before. So, deriving the virial equation of state for the real gas and taking into equation the polytropic equation, taking into account the polytropic equation, we have in general this expression of the polytropic index n, that this is general for an adiabatic process. The gas can be real or ideal. So I had a problem with the previous equation because I'm sadly just an engineer pretending to be a physicist. And when I saw these partial derivatives of pressure with volume at constant entropy, I said, okay, that's too much for me. So let's operate and see if I get something easier to work with. And then I had this thing, and I said, okay, I'm doing something wrong because this is even more awkward than before. So my supervisor said, okay, let's look for statistical mechanics. Then, okay, it's fine. Then statistical mechanics is a branch of physics that explains microscopic effects in a microscopic way. So they give me this expression of the compressibility factor that depends on the virial coefficient V, the pressure, temperature, and the universal gas constant R. And also, they give me this expression of the virial equation, of the virial coefficient, that depends only on the critical pressure and temperature that are constants for each gas, and also depends on a series of factors F, omega, that is the eccentric factor, for symmetric molecules it's 0, and well, I'm lucky because the water molecule is quite symmetric. And G is the molar fraction, that this is the part where I include the absolute humidity. And then F are a series of polynomial that depends only on the reduced temperature, that is the quotient between temperature and critical temperature. So at the end, we have an expression of Z that only depends on pressure and temperature, and an expression of the virial coefficient B that only depends on temperature. If you remember, previously I had this equation for the polytropic index, and now I have this one that is quite nicer to decide and easier. Also, we have to take into account that the specific heats now have to be calculated for the real gas. So using statistical mechanics, I have these expressions of the specific heats that depends on the ideal gas specific heats that are the one with the asterisk. I also have equivalent expressions for enthalpy, internal energy, etc., but I'm not showing them here. So this is the shape of N. You cannot see it's N. So previously it was a constant value of 1.4, and as you can see now, it's a flat surface that that changes with pressure and temperature. It's close to 1.4, but it's not really 1.4. And the important point here is that also N changes, the polytropic equation, or the adiabatic equation in my case, is still constant, and that's important because that was my starting hypothesis, and with my new equation, this is still valid. So I didn't show the equations for the entropy, etc., but I'm showing you the difference. So the first one on the left top is entropy, then internal energy, enthalpy, and finally specific heat. These are non-dimensional terms, and you can see that the different plots are for different degrees of relative humidity. So the 0% one would be the dry gas or the ideal gas, and the 1%, 100% is the real gas or saturated gas vapor. So the real gas, you can see, is more entropic than the ideal one. That means that it's less reversible. And in terms of energy, internal energy U and enthalpy H, both are different shapes of energy. And you can see that the real gas is less energetic than the ideal one. When I was doing the non-dimensionalization, I found that this term, TRPV, were always repeated. So I decided to call this the real gas non-dimensional number. And these are the limits of this number. So I think it's quite useful to compare between different gases, how real they are. Let's go for the experimental validation now. I did some measurements during my master thesis at a wind tunnel, and I inserted with a paint gun, quite rudimentary, but it worked, different extents of humidity to measure how this affected a kind of Wells turbine. So these were the measurements for pressure drop in front of airflow. You can see as I increased the humidity, the pressure drop was lower, which means a lower power in the turbine. And this was a result that at the beginning looked not important, but as you can see, as I increase the humidity, the variation between the ideal temperature and the real temperature calculated following the real gas equation differs. So what I checked is that in my wind tunnel, when I applied the energy conservation equation, the mass flow was not conserved if I use the temperature that I obtained from that equation. But by applying my new development, you can see that the inner flow and the outflow in the turbine were the same for the real gas. So with the real gas approximation, energy and mass flow are both conserved. Finally, I'm applying this to a classic OWC. This is my control volume. And I take the development done by Sheng at UCC. So what he did was dividing the cycle of the OWC in two parts. The first one, inhalation, when air goes inside the OWC. And they consider fresh air, so constant density. And the second part of the cycle is exhalation, when air goes out of the OWC. And air is considered as stale. So in this case, the density changes with time. And applying my new formulation to the equation of the mass flow through the turbine, I have these two equations of the airflow through the turbine. The terms in red are the terms that I introduced with my formulation. The rest of the equation was already given by Sheng. But also these terms in green are changed with my formulation. The first part is the compressibility effect, the second part is pressure variation, and the third is the real gas effect. So let's see this in a more graphic way. If I apply these equations to a wave cycle, a typical wave cycle, 12-second period, 1 degree temperature variation, this is the efficiency plot. So the dashed one is the ideal one, and the green one is the real. And you can see that there is a nearly 2% variation for the inhalation part, and 6% variation in efficiency for the exhalation. So this doesn't look a lot, but if we imagine a whole year or a whole life cycle, this will have effects on operation and management. And my new formulation is not only causes differences on the magnitude of the efficiency of the airflow, but also there is a difference in the phase between the real and the ideal airflow. You can see that there is a difference of nearly 20 degrees between the ideal gas through the turbine and the real gas through the turbine. So this also will affect the power extraction at the OWC. Just to finish, for my future work, what I'm starting to do now is inserting the formulation, the real gas formulation on the classical radiation diffraction problem to have a more exact calculation of power and efficiency, and also study the humidity effects along a life cycle of an OWC. I haven't shown that here because of time. I'm doing in parallel some numerical testing fluent. So I'm testing, I test an actuator disk model for just to simulate the performance of a Wells turbine. I'm applying this actuator disk model to study how the morphodynamics of the coast bed change the OWC performance. And in the future, I'm going to use this actuator disk model to test the same chamber with different degrees of humidity. There are some papers going on. And well, just to finish, the first time when Alistair told me, let's go with the statistical mechanics, I Googled statistical mechanics because I didn't know what it was. And I found this thing. So that's the first thing that appears on Google when you type it. And I said, oh my God, that's just a joke. So I researched a bit more. And then I discovered that, in fact, it's true. So at this point, I just hope that you don't want to kill yourselves because of my presentation. And well, if you have any questions, that's all. Thank you very much.
This production is brought to you by the University of Edinburgh.